So today we're going to look at static rigid bodies. This video is going to be the introduction to the models that we need to use. So pay close attention to how you can determine what sort of model you should use and then what the default diagram of the model looks like. So the notes you're taking here should have the default models and a descriptor of each of the types of questions. We're going to go through ladder questions, peg questions, and hinge questions. There is no practice at the end of this video, but it's the introduction for the next 3 videos. So immediately after this, you should be watching the ladder static rigid body video in preparation for lesson. Now, static rigid bodies come in lots of different forms, so I'll try and take you through some of the different variations, and then we'll look at how we can use our knowledge of forces and moments to solve problems involving these. So, there are many types of static rigid bodies, and we're always going to consider this as an object that has length. It's rigid, so it's not going to bend or bow. In our model, we reduce its thickness to negligible, and we're only really interested in its length. None of the other dimensions except for its length. We think about it as a rod, so we model its weight at one point along the rod itself. And this may either be at the center if it's uniform or off center if it's a non-uniform rod. Now, the context of these rigid bodies can come in lots of different forms. So on the screen, I have ladders, I have a fishing pole, I have a drawbridge, I have a cupboard door, and even a guitar. Each of these real-world objects can be modeled as a static rigid body. Okay, let's start with the ladder, which is actually the most popular type of question you'll come across. So the way we model this is we think about the wall and the floor. The ladder is going to be in contact with those two surfaces. Now, the ladder itself, we're just going to draw as a straight line. This is the static rigid body. The body has weight, so we would always try and model the weight of the static rigid body itself. And because it has weight, that means it's producing a reaction force where it's making contact with the ground. So here we have our normal reaction force, a perpendicular force perpendicular to the ground, the surface it's making contact with. Now, the ground may be rough or the ground may be smooth. If it's smooth, there will be no friction here. If it's rough, we'll have friction going in this direction. It goes against the direction of potential movement. If this ladder was to start moving, it would actually slip and slide down the wall and to the left on the floor. So friction must be going towards the right to balance out that potential slip. Not only is the ladder in contact with the floor, it's also in contact with the wall. Now there's a reaction force coming from the wall. I'll label this S. So R and S will be the two reaction forces that we have when working with static rigid bodies. And once again, the wall itself can either be rough or smooth. If it's smooth, there's no friction. If it's rough, there is friction. And once again, just think about any potential movement of this ladder. If this ladder was to start moving, it would slide down the wall, so the friction must be in the opposite direction. The friction's helping it to stay up. Okay, so apart from the angles and any other forces that we might be told are present on this static rigid body, this will be the default model, the default diagram you would always draw for a question involving ladders. As I've always said, a good diagram is going to set you up to respond to the question correctly. Okay, so the second most popular type of question that you may well come across is what we refer to as a peg question. So, in this case, the fishing rod is the static rigid body, and we'll model it like this. So, it's in contact with the ground, and it's also in contact with a support. What's important is that the static rigid body passes beyond the support. So, it's not like a wall that it was resting against, where the end point was on the wall. This passes beyond the support and even overhangs. So part of the static rigid body is beyond the support. We'll start with some of the defaults. So we know that there's going to be weight, so we can model weight, and weight is going to act straight down. Because there's weight, there's also going to be a reaction force. The reaction force on the floor is the normal reaction force. It's perpendicular to the surface we're making contact with. It's perpendicular to the floor. Now, the floor can be rough or smooth. Smooth has no friction, rough does have friction. Now, this is an important bit to get correct. The reaction force at the peg, it's always the normal reaction force that we're modeling. So, the reaction force at the peg, first let's think of the tangent. So the tangent to the point of contact with the peg is going to be a line that's right on top of the static rigid body, right in line with what we've drawn. So the normal is going to be at right angles to the static rigid body. This is the reaction force at the peg. Be careful to get this correct. Some people try to do a vertical reaction force because that's what they're used to. We state it over and over again. This is the normal reaction force. Normal as in perpendicular to the tangent. Once again, a peg can be rough or smooth. If it's rough, it has friction. If it's smooth, it doesn't. Have a think about the friction here. If this static rigid body was to move, would it slide down the peg or up the peg? Natural movement caused by gravity would make it slide down the peg, meaning that the friction should be going up. So friction is against the direction of potential motion. Okay, so the two most popular, I would say, and let's move on to third in that list. Here we have a drawbridge, so a castle drawbridge. I'm sure most of you have come across this either in films or cartoons or in some way you've seen this. A drawbridge that covers a moat. That drawbridge can be pulled up and down. It's hinged at the bottom of the castle gateway that you can see. So the drawbridge is basically a big plank that you can walk across the water, you can walk across the moat. It can be drawn up and down, and that's to stop undesirables. That's to stop the castle's enemies from gaining access. And then obviously it can go back down again for normal day-to-day access. The drawbridge has two important features that help it to move. Number one, it's hinged. It's hinged right at the bottom of that doorway. That bit of the plank is always going to be in that position while everything else moves. Secondly, it's attached by some supports, in this case these strings, or I would assume ropes or chains, that help to move the end point of the drawbridge up and down. Okay, sounds a bit complicated, but we simplify it in our model. Here's how we would model this situation. So we have the wall, we have a hinge point for the static rigid body, which is the plank, the body itself, and we have the string. Let's think of the forces that are going to be at play. Firstly, the weight is always going to be the weight. And counteracting the weight, the force within the string, within the rope, within the chain is going to be the tension. So those are the main two forces. Because this static rigid body is hinged, there are also some forces at the hinge. There's actually a two-part reaction force. Technically, it's a diagonal reaction force, but we've been working with vectors for a very long time, which describe the horizontal and vertical components of any diagonal force. So we model it as a two-part reaction force, RNS as you would expect. And here we have it, the default model for a hinge question. There is a variation on the hinge question. So there we had our static rigid body supported from above by ropes or strings. But sometimes it's supported from below with a shunt. So here you might recognize this, you might have these yourself. So these cupboard doors, they're hinged at the top and they're supported from below. Okay, how would we model this? So we'll start with the wall and the static rigid body itself, and we just need to demonstrate that the support is coming from below. Okay, let's add some forces. So we know that there's going to be weight, that's modeled going straight down. We don't have tension this time. Tension is a pulling force. We have thrust. Thrust is a pushing force. We have the thrust in strut that's holding up the static rigid body. And once again, we have the reaction, the two-part reaction force in the hinge itself. Okay, so we just set up this model and we can respond to our questions from here. This is actually a slightly more difficult than standard Hinge question. You would usually have a horizontal static rigid body. It doesn't mean we're not going to get one that's already inclined, but I just want you to know what the default usually is. Okay, so each of those 4 diagrams you should be able to produce as soon as you recognize which type of static rigid body question you're working on.